standard deviation by multiplying 2 times the standard deviation of the distribution of sample mean. That 2, again, has a special name. We're going to call it the critical value. Critical value is a number that relates a confidence level to how many standard deviations out we have to get in order to get that many of our x bars or p hats in that range. Now, because of the 68, 95, 99, 7 rule, we know 3 critical values really easy, really well. One is, if I only need to be 68% confident, I only need to be within 1 standard deviation. So the critical value associated with a 68% confidence level is 1. If I want to be 95% confident, if I want to be right 19 times out of 20, then I need a critical value that gets me 95% of all those x bars. That happens to be in a normal distribution, the number 2. The third easy confidence level critical value pair that we know is 99.7. If I want to be 99.7% confident, meaning I'm going to be right 997 times out of 1,000, then I can use the critical value 3. The more confident I am, the bigger the critical value. The more confident I am, the more values I need to encompass in my confidence interval. So, our general formula for confidence intervals is that we start with a statistic. And we're going to add and subtract a critical value multiplied by the standard deviation of the statistic. A very popular critical value is right around 2. Because that gets us 95% confidence. Go ahead. All right. 1, 2, go.
That formula is for the confidence interval?
That's the formula for the confidence interval. If you get out your formula sheet real quickly, I'll show you where it is on your formula sheet. Okay? It's on the page with the boxes. And it's the first formula on the page with the boxes. Sorry, the second formula. It says confidence interval, statistic plus or minus critical value multiplied by the standard deviation of the statistic. That's exactly what it says on your formula sheet. That's exactly what's written there. In practice, the statistic may be measured a couple different ways. Maybe we're measuring the thing by looking at a mean. So our statistic becomes x bar. Critical value, again, we're going to look at this more in the next section. Critical value is some number tied with a confidence interval. The ones, again, that we know best, normal distribution, 95% confidence, is around 2. Officially, it's actually 1.96, but we're going to say around 2 because we got the 68, 95, 99, 7 rule in our head. All right? And then the last one, the standard deviation of statistic, well, I've got written on the whiteboard, sigma over root n. What do I mean that that's the standard deviation of the statistic? In the last chapter, we had this formula. The standard deviation of x bar is sigma over root n. Oh, I'm using the x bar statistic there? Then that's the standard deviation of that statistic that I need for that formula. Hey, what about this other one? The sigma of p hat. In the last chapter, what did we learn? That this one is p 1 minus p over n. Oh, when we use p hat as the estimator, as the statistic, we're going to use sigma of p hat as the standard deviation of that statistic. So The general formula on your sheet says statistic plus or minus critical value. I know what it says. Statistic plus or minus critical value times times standard deviation of the statistic. Do you see in the boxes standard deviation of the statistic? So that's the general formula, and then they give you more information to place it in. You know what? Katja had a hand up, and I totally ignored her. So then you go.
What if they ask you like to be like 70% sure or something?
I'm going to show you how to calculate the critical values for things that are other than those three.
Yeah.
Good question. Hold that question. I'll show you how it's done.
Are all those formulas the same? A, B, C, D, E.
All of them represent the same ideas. Indeed. So people who listen to the lecture can't see them, but essentially the idea of statistic plus or minus margin of error, statistic plus or minus, estimate and statistic are synonymous. I'm trying to give you this big strain that everything looks kind of like this idea.
Really just D and
D and E is where
E.
those are the money formulas. A, B, and C are the big ideas. And actually we'll return back up to the big ideas when we do confidence interval with one other thing that's not an X bar, not a P hat. But let's wait till that happens. Are some of the things starting to click? I hope so.
Yes.
Clicking? All right. Click, click, click. All right. So again, here's our general formula. And again, we use this. We had this, so we got one more word in here. The statistic can also be called a point estimator. So one more word for, I guess point estimator and estimator are kind of the same. All right. So here are the last issues that we have to deal with. The margin of error is the critical value times the standard deviation. We get to choose at what confidence level we're going to work. The easy ones to work at, again, are 68, 95, and 99.7. But if we want to be 90% confident, I'll show you how to find that critical value. It's part of the 8-2 lecture. All right?
Why wouldn't you always just choose the 99.7?
That is an excellent question. Everyone hear a question? Why wouldn't you just always choose the 99.7?
Because you have to have a larger interval, and so it's like more sample size.
Okay, so in order to be 99.7% confident, the number, the multiplier becomes a 3, and your confidence interval becomes much greater. All right? Now, are there some things that you only need to be reasonably good at guessing as compared to really, really exact? I'm having a party. I need to buy food. Do I have to be 99.7% confident about how many people are going to the party? Or is 95% confident? Being right 19 times out of 20 is good enough. Some things need an exacting measure of confidence. Life and death decisions, for example. You need to be 99.7% confident.
So it's more difficult to be 99%.
You get a wider interval, and then the only way to make the interval smaller is to make your sample sizes larger, which costs more money. It's a trade-off. I can guess with 100% confidence that Marquise's weight is somewhere between 0 and 800. I'm 100% confident, but that confidence interval, not very useful. So to be more confident, we have wider intervals. Wider intervals are less useful. You have to decide in the context of the problem. And believe me, we will be discussing more about that later as well. Medical problems, you need higher confidence. Marketing decisions, things that aren't life and death, lower confidence. All right. All right. The critical value depends on the confidence level and how much variation there is in the sampling distribution of the statistic. Greater confidences create larger critical values, which create larger confidence intervals. If you want to be more confident, bigger critical values, larger confidence intervals, which may be less useful. Okay? And of course, the standard deviation of the statistic in both of the examples I put forth is dependent upon your sample size. Bigger sample sizes, smaller standard deviations of the statistic in both of these cases. All right? And there's a little graphic. You want to be 80% confident? You're this wide. You want to be 95% confident? You want to be this wide. You want to be 99.9% confident? This wide. Higher confidences, larger confidence intervals. Do you hear how many times I'm repeating that? That must be frickin' important.
Okay, I'll start.
All right. Star it. Double box it. All right. Any questions? No? All right. So, last part. Last part is box 2 in our 4-step process. Before you can do these calculations, you do need to make sure that the conditions for using these formulas are met. What are the 3 conditions that I've been pounding into you over the last 2 weeks? Normal distribution. We can only use z-values when something is normal. Independence, meaning that the population is much, much larger than our sample size, at least 10 times larger than our sample size, so that we get independence, and we can use these 2 formulas. Without independence, these 2 formulas are bogus. This formula is written with the idea of independence. When we do drawing without replacement, we can only do so when the population is really large, and pulling things out of the population doesn't change probabilities. There's an assumption of independence for the standard deviation of the statistic formulas. And we questioned that again and again last chapter. We want to use this here. We got to have independence. We prove independence by saying population is at least 10 times samples. Big N is greater than n times little n. What was the last condition? Unbiased. We want our sampling to be unbiased. Okay? Right. That's not the way I want you to remember it. Unbiased. There we go. And independent. I like saying unbiased because it gets at why we want random. We don't want random for random's sake. We want random because it creates unbiased sampling. So, we had all these things that we talked about last chapter. How do we prove something is normal if we're talking about a distribution of X bar? Oh, yeah. It's normal if the population is normal. Or it's normal if our sample size is greater than, what's our magic number? 30. Because then the central limit theory kicks in. What if we're talking about p-hats? Under what conditions are their sampling distributions normal? Answer, at least 10 failures and at least 10 successes. NP greater than or equal to 10, n times 1 minus p is greater than or equal to 10. And why do we do that? Because our critical values are z-values. They're coming from a normal distribution. If we use a critical value that's a z-value and we're not normal, again, we're bogus. All right. After this slide, it goes into the summary, and we're good at this point. I think I've embedded so much summary into the lecture itself, I think we're okay. All right? Does anyone have any questions before?
So 95.
No, didn't I? What I was, I want to give you till tomorrow. We're going to start A2 right now. Okay, wait, hold on. I'm going to turn off the lecture. All right?
So you guys.